Today, I'm going to host the TrustML Young Scientist Seminar. I'm Jin Feng, researcher in Riken EIP. Today, we have our valuable guest, Professor Bo Li from UIUC. Professor Bo Li is an assistant professor in the Department of Computer Science at the University of Illinois. Champion. She is a recipient of many awards, including AGK Computer Thought Awards, Alfred Sloan Research Fellowship, SF Career Award, and even the MIT Technology Review Award. And she also the recipient of many best papers at several top conferences in machine learning and security, which is a remarkable success. Her research focuses on both theoretical and practical aspects of trustworthy machine learning, security, privacy, and game theory. She has designed several scalable frameworks for trustworthy machine learning and privacy-preserving data publishing systems. Her work has been featured by major publications and media, such as Nature, Wired, Fortune, and New York Times. Let's sincerely welcome our today's guest, Professor Bo Li, to give us her talk, Trustworthy Machine Learning while Learning with Reasoning. Yes.
Okay, yeah, thank you. Thank you for the nice introduction, Jinfeng. It's great to share our recent research about trustworthy machine learning here with everyone. And today it's a very, very new talk because I know it's a winter break and everyone start to think about the next step and things. I actually was doing some like new research thinking and new direction thinking. So this is actually something I made recently for the next new research generation. So I think it will be interesting. And if you have more questions, we can discuss. So let me jump right in. We know that machine learning is ubiquitous. I don't need to mention too much about it. Has been used in autonomous driving, like ChatGPT recently, and intelligent speakers and diffusion models, all the fancy and nice applications. However, we also see that there are a lot of concerns happened in different autonomous machine learning applications. For example, it keeps having different car accident for autopilot. For the large language models, either it has biasness or it can leak private information. And for the very nice generative models, and it always say we face the threat of deepfake and generating adversarial malicious content. And those things has been keeping us day and night, and a lot of news report and real world like threats has happened and have been like causing a lot of concerns for the large deployment of machine learning models, right? So for in particular, in our group, we have shown or demonstrated several adversarial vulnerabilities in real world. For example, maybe you have seen these types of optimized stickers on the stop sign can exactly manipulate the autonomous vehicles to misrecognize it as speed limit sign 45, which is a targeted attack. And then in a dynamic environment, you can drive a car towards it and it will completely fool the recognition system of the autonomous driving, and not only in classification scenario, white box, but also in black box and against the object detectors. And still you can see that the stop sign itself can never be recognized, even though all the other object can be correctly recognized. And this is under the black box setting. And not only about this, but also against the real world commercial like LG and Apollo simulation platforms for autonomous driving. And the autonomous driving vehicles is equipped with the sensor fusion systems. And even for such sensor fusion systems, you can see the car will exactly run into the object without being able to recognize it, which is very dangerous in these types of real-world commercial simulation platforms. And such adversarial perturbation has also been exhibited in the Science Museum of London and raised a lot of social concerns. And not only against the autonomous driving application, right, but also against other very safety critical scenario, for example, medical, right? So in this simple example, you can see this is MRI data, and if you do automatic segmentation of it, it's perfect, can segment the contour here. But if it's an adversarial scenario, you can easily manipulate it and no one can see the difference of it, but you cannot segment anything out, which is pretty dangerous. So with all these threats in the real world, we have seen our lab mainly focus on designing the certifiably robust, private, and generalized machine learning paradigms for different real world applications. And to achieve this goal, we mainly focus on close the trustworthiness gap between different distributions. That's the fundamental question or problem we are trying to address. Why we say it's fundamental? Because from different perspectives of trustworthy machine learning, for example, robustness, you can see that actually you can view this as a distribution drift between the training and testing, which means in terms of like testing time attack, it means the attacker will manipulate the testing distribution explicitly. And in the training time attack, the attacker will be able to manipulate the training time. And this means under the trustworthy robustness, we want to explore different threat models, training time, test time, and different constraints of the attackers, and then trying to leverage game theoretical analysis to improve the or defend against those attacks and provide certified robustness for different ML models. And similarly, from the privacy perspective, we want to similarly to explore the privacy attacks to understand the attackers' behaviors, the strategies, cost, utilities, etc., and then therefore design the privacy-preserving data generator models for generic tasks or privacy-preserving learning algorithms for specific types of important learning algorithms. And similarly, from the generalization perspective, we can see we can view the adversarial distribution shift here from the robustness as a natural distribution shift from in the generalization perspective, and uncovering its relationship between robustness, privacy, and provide the certified ML generalization, which is one of the goals of machine learning. Right, and not only about the individual pillars of those work, but also their underlying connections are also very important. For example, we were able to prove that if a model is epsilon delta differentially private, you can actually represent the certified robustness as a function of epsilon delta to make the connection between these two. And we can also prove under certain mild conditions, the robustness, adversarial transferability, and the domain transferability are bidirectional indicators. So to make underlying connections between the pillars. So this is very important because those underlying connections can help you to avoid reinvent the wheels and also get in-depth understanding about different aspects of trustworthy machine learning rather than just study them independently, right? So in this talk, we'll mainly focus on the robustness pillar due to the time limitation. And if we expand the robustness pillar, these three layers concretely, we'll see this is marriage between the algorithms and the real world impact and industrial applications. For example, from the threat model perspective, we have been doing and the community have been doing since 2015 about different physical attacks, as I shown you before, and the spatial and the unconstrained attack, which means you don't need the perturbation to be very small magnitude. It can be arbitrarily large. For example, you can change the color, you can change the texture, which can be visible but still stealthy, right? And of course, black box attack against the real world APIs, which is very important in real world. And based on such threat model exploration, the most important thing is trying to provide defenses and hopefully with certain certifications, right? And here with the certification is based on certain data and model properties, like the game theoretical interaction properties, like spatial and temporal consistency of data, and model consistency and smoothness from the model perspective. And finally, also hope to leverage additional information such as domain knowledge and logical reasoning capabilities and integrate those into machine learning models or into those pure data-driven models, such that we can provide better or higher or more significant improvement for the certified robustness for different machine learning models. And along all of them, there is a line of deployment of different algorithms in like autonomous driving companies, in like for several computation first price, and some techniques here have been deployed in IBM, Amazon, and eBay, etc., etc. And in this talk, I'll mainly focus on this part, which is, to me, I think is very promising and can lead to a lot of interesting future work as well. So in order to understand like what types of certification or robustness or algorithms we need to propose or analyze, right? We first need to understand how to measure the ML robustness, right? How do we say one model is more robust or less robust? And what do we mean by giving guarantees for robustness of ML models, right? So we can see over the years, to improve the robustness of ML models, there are different empirical approaches like proposed to improve the robustness. And all these lines here provide empirical robustness improvement algorithm, for example, also training, for example, ensemble models, etc., etc. But we can see one like bad news or unfortunate news is that these types of empirical robustness measurement, which is by leveraging the model, like evaluating model accuracy against the different attacks, can be adaptive attacked again, which means if you have new attack models, maybe it will be able to break all those defenses again, which is not what we want, and lead to the traditional security and cat and mouse game. And we hope to mitigate that. And therefore, we need to provide certain certified robustness for, say, deep neural networks. And the certification of robustness on the high level means that the lower bound of the model accuracy under certain constrained attacks. And slightly more concrete, it means we want to solve the min-max problem such that we can get an upper bound of this loss or the lower bound of accuracy here. So basically here, the given a model parameterized by theta, your x is a original instance, by delta represents certain perturbation. This perturbation can be additive, can be transformation, can be any format, right? And here we have a distance to measure the adversarial constraint, like how large or how what's the cost of the attackers need to pay if they perform such attacks. And to solve this min-max problem, we exactly get the lower bound of the accuracy of the model, and that lower bound is called the certified robustness, which means if I tell you that this model, the certified robustness is like 90%, which it means that no matter what types of new attacks you have, as long as the perturbation is constrained by certain magnitude or certain format, then you will not be able to attack the model accuracy to be lower than that, which provide a very rigorous guarantee and make it more confident for human to deploy the machine learning models in real world, right? So over the years, there have been different efforts, including our group and including from the communities, to provide different certification for robustness. And this is a brief overview of the categories of the different certification methods, including deterministic, probabilistic, and different relaxations to solve this min-max optimization problem, right? And correspondingly, there are different robust training algorithms. So we can see these types of certification is rigorous, which is nice, but it's also expensive, right? For example, if we use mixed integer linear program here, we can just scale up to like at most 2,000, 3,000 neurons, which is far from the models that is useful currently, right? And also many, it could be loose in many cases because it's have layer by layer relaxations, etc. So then this is like on the high level, we can see there are some drawbacks, right, of existing certification method. And more quantitatively or concretely, we can see from different data sets, we can compare the state-of-art robustness we can obtain recently. For example, on MNIST, if we give, say, our infinity norm bounded by 0.3, the certified robustness is about 93, and the empirical robustness is about 96, which is like a small gap, which is nice, right? Which means on the small data set, such as MNIST, these types of certification is more or less like achieved. However, when we just scale up the data a little bit, for example, on CFAR, the certified robustness so far is around 40, and the empirical robustness is 68, which still have a large gap, meaning that either we need additional tighter certification approach to increase this number, or we need to explore more powerful attacks to reduce this number, to minimize this gap, right? And of course, if we go to a larger data set like ImageNet, this gap is even larger, and which means the existing certifiably robust approaches have achieved the bottleneck and very hard to scale to real data set. For example, ImageNet, 30% is almost useless, right? So this leads us to see and think whether we can like propose or understand better on robust training or machine learning approaches to improve the certified robustness. Yeah, I can monitor the questions and welcome if you have any questions from the chat. So then, in order to provide better or significant improvement of certified robustness, one thing we may think about is, can we leverage domain knowledge and logical reasoning to enhance the certified robustness of ML, right? Because from the previous example, like the very well-known stop sign example, you can see for human, you cannot be attacked, right? But machine learning model can be easily attacked. And one potential reason of that could be human have the domain knowledge, you know, it's an octagon shape, it's red, then it should be stop sign, etc., etc. So can we integrate those like knowledge and the reasoning capabilities of human into the current data-driven models to improve the robustness of it, right? In a principled way, of course. And here I want to introduce one framework that we proposed to, I would say this is one way to achieve this goal, and there could be other ways. And I would say that we'll hope to have other, like the whole community's effort to jointly work on this. So on the very top level, you can see the way to integrate domain knowledge and reasoning component is that we compose a framework called sensing and reasoning. And in the sensing part, we have different statistical data-driven models. For example, neural network or SVM or deep neural network, and in any models you like. And here we take the output of different models as an input of a reasoning component. And this reasoning component can be realized by different graphical models, for example, Markov logic nets and Bayesian nets, which can represent the domain knowledge with their graph structure, and then provide or perform the reasoning ability or understanding for the prediction here. Then with this end-to-end pipeline, we'll be able to certify the robustness of this end pipeline, which means given the input perturbation constraints, will certify the output robustness prediction upper lower bound, right? And the intuition of such a framework or pipeline is that it should be hard for the attacker to attack every census here. And not only that, but also they need to still preserve their logical relationship, right? This is pretty hard. And the goal here is to upper bound the end-to-end marginal prediction probability of which is here. And the challenge, of course, is to solve the min-max of this pipeline. As we mentioned before, for a single neural network, if you want to provide certification of it, you want to solve the min-max of a single neural network, right? And here, given this pipeline, we need to solve the min-max for this whole pipeline, which is more challenging. And we'll see how we can do it. And to give a very brief example here, you can see the sensing part can be represented as given the input, you send it to different sensors, say this sensor tell whether it's a dog, it's a cat, it's an animal, and the knowledge represents, say, dog belongs to a cat, animal and cat belongs to animal, etc. And then here we have different predicates to predict different models. And then we have different factors from the reasoning here, and the factors will be learned based on the weights of the factors will be optimized. And we'll discuss how concretely later on we can train such weights and train the end-to-end pipeline here. So here is just the example. And by doing this, we want to see whether or not this pipeline should work, right? And qualitatively, we want to see that here is two examples. Left-hand side is a dolphin and right-hand side is a panda. And then we can see the dolphin, given a neural network model, it can correctly classify it, which is great. But if we attack it at probation, it will misrecognize it as panda, right? And the other bars show the prediction of different sensors here. And in the end, you can see if with like such a pipeline, this attack will not succeed because we can see the dolphin will be recorrect. The reason is that because of those like sensors, which can recorrect the prediction confidence of the sensors, then in the end, the sensor will automatically output the correct prediction. So this is a high-level intuition and see how this pipeline should work, right? And more concretely, we will have several questions to answer to better understand such a pipeline, and that will be the main focus of this talk. So first of all, given such a pipeline, we have three questions want to ask. First is, how can we certify the robustness of a reasoning component here, right? Because we know we can certify robustness of a single neural network as we've shown before, but with such a complicated end-to-end pipeline, how can we certify them? Most importantly, how can we certify MLA itself, right? And second of all, we want to know whether or not such a pipeline will indeed improve the robustness compared with a single model. Can we prove that? And can we lay out what's the sufficient conditions we need to satisfy such that such a pipeline will always be more robust than a single model, right? But in the end, we of course want to scale up such a pipeline and apply it to different domains, data sets, problems, and we can see how generalizable it is, right? So first, let's look at the first question. So basically, again, take the example we shown before. We have this pipeline from end to end, and then we have sensing and reasoning, and we can learn the weights of the reasoning component here, right? And here, the weights have two types of factors, the interface and the interreal factors. And in order to provide the certification of such a reasoning component, what we want to do is exactly trying to upper lower bound this quantity, which means here the Z1 is the correct assignment of the graphical model here, and Z2 represent all the possible words. So this probability itself represents the marginal prediction probability, and we exactly want to get the upper lower bound of it so that we'll get a certification for our reasoning component, right? So this is a problem we'll try to address. And more concretely, since this is a graphical model and the Z1 exactly equals to the weights multiply the factors here, and similarly for Z2, right? Just Z1 has the correct assignment, Z2 represent all the possible words, right? And in order to do this, let's see how hard it is before we start to do it, right? So we know there's a famous problem called counting, and we can actually write the robustness certification problem we have similarly in the counting problem here in a similar format. And therefore, we can directly reduce the counting problem to the robustness problem, and then prove that the robustness problem that we want to address is Shapi complete, which means indeed we definitely cannot have a polynomial time algorithm to provide a certification for MLM, which is a bad news, but it at least tells us how hard this problem is, and we should not spend a lot of time looking for polynomial time algorithm, right? And after that, want to see whether or not we can make some approximations to understand or derive the certified robustness of MLM given its complexity, right? So here, concretely, we can see in order to calculate the Z1 divided by Z2, as we mentioned before, we can take a log for Z1, Z2, right? So essentially, when you take a log, it becomes the subtraction, and the max will exactly taken at the max minus mean, and the mean will taken at the mean minus max, right? And the Z delta here is approximation of the ground truth D, which is the output of MLN, plus certain bounded epsilon. Epsilon is magnitude of perturbation, and lambda is certain coefficient. And very nicely, we can see that with such a framework, we can prove when the lambda is larger than 0, this D delta is always monotonic increasing or monotonic decreasing, which means the max and the mean can be exactly obtained at the 2 points, right? And when lambda belong to -1, 0, we can prove the Z delta itself is always convex. Therefore, we can always get the mean or max at the using the first order and at one of the points of the minus C and C here, right? So this means we can exactly approximate the lower bound and upper bound of the prediction probability of MLN, and it therefore provide the robustness certification for it. And with such a result, let's take an example. Take a look at the example and see how tight such a bound could be, and whether or not it can improve the certified robustness for, say, realistic deep neural networks, right? So here's one example of primate net, which is part of the ImageNet. And the goal is to predict different categories of primates, for example, apay, great apay, etc. And there are two types of knowledge we can use. One is, say, the hierarchy knowledge, meaning that if a sensor predict the input is great apay, it must be apay, right? And exclusive knowledge, meaning if a sensor predict it is a great apay, it cannot be laser apay anymore, right? So we can easily represent these two types of knowledge as first order logic and embed it into MLN. And concretely, we can take a look to see that in terms of benign accuracy, that very surprisingly, with knowledge, we know that usually in any machine learning models, there will be a trade-off between benign and the robustness accuracy, right? But here, because we integrate additional information such as domain knowledge, not only the benign accuracy is not dropped, it's slightly improved compared with without knowledge, right? But also the certified robustness is dramatically improved, which means that there is no trade-off between benign accuracy and certified robustness anymore for such sensing reasoning pipeline, which is pretty surprising and nice. And from the certified robustness, you can see the improvement is about 30–40% compared with without knowledge, which is quite significant because in terms of certified robustness, usually 3 to 5% is already quite large. And here is it achieves 30 or 40%. And this shows that it is very promising to integrate domain knowledge within such a sensing reasoning framework. And we show we are able to provide certification for MLN and therefore provide certification for the end-to-end pipeline. And we can see the significant improvement of the certified robustness, and there is no trade-off or like harm to the benign accuracy, which is very nice. And next, we want to say now we know how to certify this. And we also empirically see that their certification is indeed improved, right? But we still want to understand whether we can prove their certified robustness is indeed always higher than a single model, right? And under what conditions such property is true. To answer this question, let's still take a look at the example of stop sign. And here we can see, given this stop sign as an input, we have different sensors, and the stop sign, recognize what sign it is, and this recognize whether there is a stop pattern in it, and this recognize whether it's octagon shape. And what we have knowledge here is that two directions. One is if the main sensor predict its row sign, like the octagon sensor must predict it to be octagon, right? And on the other hand, if there is a pattern here of stop, it must mean that this sign is a stop sign. Basically, two directions of the knowledge, which we call it permissive and preventive knowledge. And to understand, the reason to have this two direction of the knowledge is that, therefore, based on these two types of knowledge, we can exactly characterize the truth rate and the false rate for different sensors. For example, let's use alpha to represent the truth rate and epsilon to represent the false rate. And therefore, based on such analysis, we can actually, first of all, get a theorem result to show that such pipeline will exactly have a lower bound of the accuracy. So this is a pipeline. The pipeline have a lower bound accuracy like this. And here we can see the lower bound itself depends directly on the contribution of the different sensors. For example, as long as mu is larger than 0, meaning that the additional auxiliary knowledge sensors contribute to the main framework, then such a pipeline will have a lower bound of the accuracy, right? And based on such accuracy lower bound, let's compare it with the accuracy or robustness of a single model and see what we can get, right? Basically, the sufficient condition is that if we want such a pipeline is more robust than a single model, like the main model itself, this condition need to be satisfied. And what this condition means is actually very intuitive and interesting. So we can see the gamma here is represented as alpha star, meaning the truth rate of the main model, and alpha k and the epsilon k, meaning the truth rate and the false rate of the knowledge models. And we can see here, if this is super large, right, then this gamma is very large, and then this condition is like this on the right hand side is also very large. So this is not that easy to satisfy, which means that if the main task have perfect truth rate, like very large alpha star here, right, it is not impossible, it's not possible to improve, which makes sense if you have a main sensor which is perfect already, so there is no room to improve it, right? On the other hand, if the knowledge sensor contribute, basically the truth rate is larger than the false rate, and this quantity is very high, then this gamma will be very large. You can see this gamma will be very large. And if the main sensor is not perfect, it's small. And if this is small, this right-hand side is relatively small, and this condition will be easy to satisfy. And therefore, the whole pipeline will be better than a single model, which means as long as the knowledge sensors contribute enough useful information, you will always achieve a higher robust pipeline than a single neural network model, which is very intuitive, but actually we can concretely write it down and show it is true. I think this is very nice. And based on such a result, we can see one additional property of such pipeline is that it is data and attack and task agnostic, right? So it's possible to test such a pipeline against different attacks. For example, here, first of all, we want to show the clean accuracy. And like before, we can see the clean accuracy here, there is no trade-off, and the pipeline always achieves slightly higher clean accuracy, which is nice. And on the right-hand side, the x-axis shows all types of attack, including infinity attack, like semantic attack, physical attack, all kinds of attack. And you can see the bar, the positive bar shows the improvement of the pipeline compared with a single neural network. And you can see the bar is always positive with very high, meaning that it's achieved much higher robustness than a single neural network model for this pipeline. And concretely, let's take a look at some examples. For example, if we apply such a pipeline against the physical attacks, the improvement is quite significant in terms of both clean accuracy and robustness. And if we test it against other, say, L infinity attacks under different epsilon, sometimes there is a small trade-off for clean accuracy, but for robustness, it's always much higher significantly. And we can test it against unforeseen common corruptions, including like fraud, contrast, brightness. So note that this is just a single pipeline trait. It's not adapt to any attack here. So directly just use any attack to attack pipeline, right? And the pipeline is always more robust than a single neural network or than a state-of-art method. So with this, we can see now we know how to certify it. And we also know under certain conditions, which is the knowledge sensors contribute enough useful information, such a pipeline is always more robust than a single neural network, right? And then next, we want to see how we can make such a pipeline scalable and apply it to different domains and see whether or not indeed it's useful in practice, right? So concretely, we can see currently the inference of ML itself is sharply complete, and we want to approximate the inference efficiently, right? And one thing, somehow it doesn't show. One thing we want to show is that we can use variational inference to make the the approximation and use GCN to incorporate the knowledge. And we know the inference of GCN is very efficient, and therefore we can leverage GCN to perform such prediction. And then the question is how we can train a scalable GCN to represent the MLN we have, right? So here is one simple example. So basically we can see, given the input, still we have different sensors to predict whether it has flippers, whether it is fury, etc. And we can represent these knowledge sensors and connect them based on their relationship. For example, if it is a panda, it should be furry. If it's a dolphin, it should have flippers, etc., etc. And we connect such like a sensing and reasoning with the structure of GCN. Basically, it means that if different nodes in GCN represent different sensors here, and if they have a relationship, we'll connect them. And such a GCN structure will be intuitively learned in terms of the weights of the knowledge rules and the weights of the GCN itself using EM. So concretely, it means that here we have a variational posterior of different sensors, right? And then when we learn the weights here, in the E step, we actually can learn the the GCN parameters by fixing the weights. And in the M step, we fixed GCN's parameter and learn the weights of the rules. And intuitively, it will converge, and we will have a GCN which is parameterized to represent the knowledge rules here. And in this scalable framework, we'll be able to show its performance under different application data set and scenarios. For example, here, in this GTSRB, like the road sign, we can exactly represent the sensors and the component, and we can map it to a GCN structure, scalable structure we mentioned, and perform the analysis. And similarly, for this data set, like Word 50, it has different letters, classification, and the knowledge we can use is that the three position will decide a letter, and the different positions, the word will decide what the letter should be at the different positions, right? And these are two examples in terms of CV image classification. And since such a pattern is agnostic to applications, so we can see not only CV tasks, but also NLP. For example, in this case, this is an example of stock price prediction. And the sensors we use is that the main sensor of the stock price, and the later sensors represent whether the price change, whether the price is gain or lose, etc. And the knowledge itself we use is a simple arithmetic rule. Basically means that the stock price over the day, like the increasing and decreasing, should add up based on their final price, right? And this is example in the NLP case. And another example is in the PDF malware classification. So basically here, you can represent this input, which is a PDF malware, with different sensors. For example, the main sensor predict whether it's a male whale, and other attribute sensor predict, say, whether you contain such a feature, or you contain different features. And the knowledge means if you are malicious, usually you will have certain pattern of features, or the feature themselves have some relationship. For example, the children feature always indicate the existence of some parent feature, right? So basically we can construct such knowledge and still build up the scalable sensing reasoning framework we have. And here I want to show one quick example to see how the improvement is. Here is the example of the row sign and compare with different types of models or baselines, swing, smooth ADV, and consistency. They are the state-of-art method, and we can see the certified robustness and including the bin accuracy that the CARE, which is the pipeline itself, always achieve the best. And against the different like AWA, the animal data set, the Word 50 we mentioned, and GTS-RB, they always improve. And even in terms of empirical accuracy, meaning that you directly attack them, and the empirical accuracy is also improved. And such knowledge is not only useful for, say, classification models as we shown before, but also for lots of other scenarios. For example, here is a generative model that you want to generate the safety critical scenarios to train autonomous driving vehicles. And we have developed knowledge-enabled safety critical generation by using a tree structure to represent the locations of different cars, and therefore enforce the physical location constraints or knowledge to the driving, like autonomous driving vehicles, and therefore generate the safety critical scenarios, which is more realistic. And we also, there are different types of knowledge we can use, right? And not only about those common sense knowledge we mentioned before, but also we can do intervention and to identify some causal relationships and use those causal relationships as knowledge and generate safety critical scenario and use those to train autonomous driving vehicles, which show that it's dramatically improved the robustness of the autonomous driving vehicles as well. So with this, to show that based on all the pipelines and the understanding we mentioned, there are different useful frameworks I want to mention here, and hopefully that will be useful for for many of you. For example, here we'll provide, as we mentioned, like safety in autonomous driving. Here is a unified platform to generate all kinds of different safety critical scenarios for autonomous driving, and there are, I think, currently more than 3,000, and there are more. And we also host the autonomous driving safety computation in both CVP and NIPS. And here are two like certified robustness for reinforcement learning against both training time and testing time attacks. And such certification can be evaluated or provided for NLP tasks and for federal learning, etc. So in the end, I want to use these slides to conclude as well, to show that indeed, in terms of trustworthy machine learning, we have different perspectives and people are working on different things, but there are not only individual pillars, but also their underlying connections are very important. And it would be important to understand the trustworthiness itself as from a holistic framework and driven by fundamental research, focus on not only each individual pillar, but also their underlying connections before the large deployment of machine learning algorithms or models in real world. Okay, yeah, thank you, everyone. Happy to take questions.
Thank you very much. Hello, everyone. If you have any question, please feel free to ask. You can open your mic to ask, and also you can type it in your chat box. By the way, I have a questions. Right now, I saw some papers designing some adversarial attacks on decision trees. So would this technique could be employed to do some attacks on your reasoning parts? So make this framework fail?
Yeah, that's a very good question. So indeed, for decision trees, basically you have the kind of some tree structure, and you can say, you can imagine they have a gradient and you can approximate the gradient and then attack them, right? But here the reasoning is that you have the relationship. So you, if you attack some of the models, the output will violate their relationship. So the relationship will be checked. It's not so decision tree, I would say, is still a data-driven model. It's peer fitting the model. You can approximate gradient, but here you cannot exactly approximate the gradient here, because once the input changes, all the output here will change and the relationship will be violated. So directly attack using the say gradient approximation or black box attack to attack APIs or decision trees may not be applicable to the reasoning component, because it's construct the real relationships that can be actually used as an explanation for machine learning models.
I see. Thank you. Tai, do you have any questions?
Yes.
Yes.
So could I have a very small question? Yes, first of all, I would like to thank you very much for a very well-structured presentation, very interesting. And about this slide, so I have a question about the way we ensemble the model, and with the logic module as you propose. So I feel that in the laboratory environment, it kind of a perfect strategy to deal with the to combine the multiple neural network to have a better performance. However, in the real life scenario, I concern that when most of the machine learning model produce the wrong prediction. So in that case, do you think that the whole ensemble system can be tricked to produce some wrong prediction?
Mm-hmm. Yeah, that's a good question. Indeed. So this is, although we have many, say, models here, it's not just a simple ensemble, because they have relationships. That means if we attack all of them, but it's very challenging to attack them such that they satisfy all the relationship. For example, if it's like a dog, I attack it to a cat, but this I attack it to a dolphin, and their relationship will still not be satisfied. For example, a dog doesn't know how to swim, and then if you attack a dolphin to a dog, for example, so this rule will be violated, and it will use the knowledge rule to recorrect and recorrect the prediction confidence of those sensors. That's the thing. But indeed, if we attack all and we satisfy all the logical rules, then it will be attacked. But that will be very challenging, because sometimes such space may not even exist.
Yes, thank you very much. So I have imagination that because we're working on the digital machine, so if someone intentionally produce some kind of device to learn on the strategy to attack the system, just using some kind of adversarial techniques. So do you think that it could be a risk in the future?
I see. Yeah, that's a good question. And that's why we want to provide the certified robustness. First of all, with the certification, it means it already provides you a lower bound of accuracy of such a pipeline. So if you have new attack in the future, new types of attack strategy, as long as those attacks satisfy certain constraints, for example, my perturbation need to be bounded, or my transformation need to be bounded. Because if it's arbitrary powerful attacker, I think there's no system can defend, indeed. But if the attacker satisfy constraint, it doesn't matter it's a new attack or new strategy, it will not get attack the system to be lower than that certification. That's why the certification itself is very important. Yeah, and second of all, because of in terms of the certification, we can see such a pipeline improve significantly, and that means it provides confidence to improve the lower bound. And therefore, if the lower bound is high, then you can at least be very confident your model will be robust in the future under this type of attack constraints. Yeah.
Yes, thank you very much. I just have on the last question. I guess the content of your talk today. Do you have any kind of publication so that I can read it? Yeah, I think it's very interesting. So it's
Sure. Yeah.
Yes.
I will send the link. Yes.
Yes. Thank you very much.
Thank you.
All right. Thank you very much. If there are no further questions, let's conclude our today's seminar. Thanks again for Professor Lee. Give us a very exciting talk. Hope you can visit us in the future.
Yeah. Thank you. Thank you, everyone.